Okay, welcome back. It's my great pleasure to introduce Professor Johannes Sprang from University of Duisburg-Essen. Professor Sprang is a recipient of Frontiers of Science Award, and he'll talk about algebraicity of critical Hecke L values. So let's welcome him.
So thank you very much for the nice introduction. It's a pleasure to be here at this very nice conference. So today I would like to talk about algebraicity of critical Hecke L values, and everything is a joint project with Guido Kings, and it's based on this paper for which we were awarded this Frontiers of Science Award. And I would like to begin with a very basic and very elementary introduction with the Riemann-Zeta function. Of course, you all know the definition of the Riemann-Zeta function. And it admits an analytic continuation and satisfies a very nice functional equation relating s to 1 minus s, but you have to introduce these gamma factors at infinity. And in some sense, the question about special values of L functions even predates the first definition of an L function and even the definition of the Riemann-Zeta function, because already in, I guess, the 17th century, people asked the question about the value of this series. Maybe I just write down what we nowadays call theta 2. So they were aware of the convergence of n bigger or equal 1 over n squared, and they asked what is the value of this series. And it took almost 100 years till Euler somehow solved this problem, but even better, he did not just compute what we nowadays call theta of 2, but he computed this for all even exponents here. And the answer is something you, of course, know. It's essentially we have a power of pi or of 2 pi I, and then we get rational numbers. And now we can use the functional equation, and after applying the functional equation, this formula in some sense becomes even nicer because some of the powers of 2 pi I disappear, and we just get a rational number. And another fact which is worth to mention here is that this formula here, so this side here only applies for positive even integers, but the right-hand side applies actually to every non-negative or to every positive integer. So this formula theta 1 minus n is given by this formula applies to any non-negative integer. And so you might wonder, okay, if we have this formula for all, say, negative theta values, why can't we apply the functional equation once again to deduce a closed formula, for example, for theta 3 or the odd theta values? And of course, the reason is that these gamma functions, these Euler factors at infinity, which are essentially given by the gamma functions, have poles at the corresponding values, and so we can't use the functional equation to say anything about odd positive a. And in some sense, this led delineates to the definition of critical L values for general L functions. So a value of an L function, so in this case, the value of theta s is called critical at s equals n, if neither of these gamma functions has a pole at s equals n. And otherwise, the value is called non-critical. And now let's just somehow look at the poles of the gamma function. They are here, in this case, by 0, minus 2, minus 4, and minus 6, at least if we normalize this by s over 2, as it appears in the function equation. And so the non-critical values, so the values where there's a pole of the gamma function are here, and symmetric with respect to the symmetry axis. And the critical values are exactly the values where we have Euler's formula, so theta 2, theta 4, theta 6, and the other values on the other hand of the function equation. And we can now reformulate Euler's formula as follows. So we have this critical theta value, we divide it by a certain period, and we get some, say, rational number or algebraic number. And this immediately raises two questions, which are, I would say, maybe the guiding questions of my research. So what can we say about non-critical theta values? So what can we say about, for example, odd theta values? Things like irrationality. But I don't want to talk about this question. Today I would like to talk about generalization of Euler-type formulas, so formulas of the form a critical L value divided by a certain period is algebraic. And this has been formulated in a very general form by Deligne in this conjecture. And I would like to answer this conjecture today for, in some sense, L functions of, or Hecke L functions. And so let me briefly recall the notion of Hecke characters of Hecke L functions and then state our main theory. So a Hecke character is just a character, so a continuous homomorphism from the Edel class group to C star. And we can associate a conductor to such a character. So the conductor is just the smallest integral ideal f in OK, such that k factors through this quotient. And let me now say how this UF is defined. This is a certain congruent subgroup. It's just given by the kernel of the reduction mod f. Okay, and the smallest such f is called the conductor of the character. Okay, maybe I should say here that I'm somehow ignoring the infinite places, but for the reason that later on we are mainly interested at totally imaginary fields, and there are simply no open finite index subgroups of C star, so we can ignore the infinite places for our main theory. Okay, otherwise you might maybe also want to use in the conductor also somehow the infinite places. Okay, so what is an algebraic Hecke character? An algebraic Hecke character is a Hecke character where somehow the behavior at infinity is somehow given by some element of z to the jk, and jk is just a set of all embeddings of k into c. And let me make this more precise. So a Hecke character chi is algebraic of infinity type mu. Mu is this element here. If and only if the behavior at infinity, so we restrict it to the infinite ideals, is given by just applying sigma to the element alpha, which means that we apply sigma to alpha and raise it to the power minus mu of sigma. And it's easily seen that chi is a finite character, so it's just finite. The image is finite if and only if k has infinity type mu equals 0. And let me give first examples of Hecke characters. One simple example is just a norm character. We can simply take here the product over all local norms. And this is, of course, in the end a finite product, because by the definition of an ideal, somehow at almost all places we have here local units. So this product is in the end finite, and it makes sense. And of course, k star is in the kernel by the product formula. And the next example is for k equals q. There we can make Hecke characters more explicit, and you will see that in the end you just get Dirichlet characters multiplied with the norm character, because we can somehow write this ideal class group as the units of z hat times r bigger than 0, and then we just have to study characters of this group and this group, and characters of z hat star always factor through some integer f, so we just get characters of, say, z mod f z star, which are just Dirichlet characters, and characters of r bigger than 0 are always more or less responsible here for these powers of the norm type. So you can see that every Hecke character is essentially a product of a Dirichlet character and these norm type characters. And so in a few slides, we will define somehow Hecke L functions. So one class of examples of Hecke L functions you can think of, if you haven't seen them before, are just Dirichlet L functions. And so we also have this notion of algebraicity for Hecke characters, and this character of this form is algebraic if and only if S is contained in the integers, because the only infinity type comes here from the norm character, and the norm character, of course, has infinity type 1, 1, 1, 1, so 1 at every infinite place. Okay, and now we would like to define the notion of an Hecke L function, and therefore we first want to say how we can take a Hecke character at some, say, a fraction ideal f, so that we be a place which does not divide f, and f is the conductor of our algebraic Hecke character. Then let's choose just a prime ideal corresponding to this place, and let pi v be a uniformizer in the local completion. And then we just simply define chi of pv of this prime ideal as the value of chi at the ideal, which is almost everywhere 1 except at the place corresponding to our fixed place where we put the uniformizer. And this is well defined. Of course, the uniformizer could somehow be twisted by local units, but by our definition that v does not divide the conductor, the local units at v are all in the kernel, and so this is really well defined. And then we can simply define chi of a for fractional ideals by multiplication, and can define the values of Hecke characters at fractional ideals, which are coprime to f. And this also leads to a more classical definition of Hecke characters, which is sometimes useful. You can alternatively view Hecke characters as multiplicative maps from fractional ideals coprime to f to c star, which are again on principal ideals given by the infinity type in this sense, that it's just the generator to the power mu, which means apply sigma to xi and raise it to the power mu of sigma. And here you already see something. we will see in a second that not every infinity type can appear as the infinity type of an algebraic Hecke character, because if you look at this formula, it means that you have here, this formula holds for any choice of this generator. So if you twist it by units, it means that the infinity type has to kill the units. And so if the number field has many units, this gives somehow many restrictions to the possible infinity types. Okay. And now let's just define the Hecke L function as more or less the sum of k of I divided by n a to the s, or you can also write it here, it's an Euler product in this form. This converges for r sufficiently large, but then again we can somehow add certain Euler factors at infinity, and then the corresponding L function satisfies a nice functional equation, again relating s to 1 minus s, but here we have the character and here the inverse character. And one nice feature of these Hecke characters, if we not only work with finite Hecke characters, but with all Hecke characters, is that we always can twist somehow, we can always shift somehow here the value s in the character by using the norm character. This is very useful because if we are now interested in studying all, say, algebraic Hecke characters at all integers, then we just have to study them at s equals 0. So we can always use this formula to shift the s here into the character, and then we just have to study Hecke characters at 0. Okay, and again, we have now the notion of critical Hecke characters. Now, using this observation, we can define somehow being critical for the character itself, because from now on, we just take the value at s equal to 0. And so we say that an algebraic Hecke character is critical if neither of the somehow Euler factors at infinity has a pole at s equals 0. And now it's not difficult to see, so I haven't told you how these gamma factors or these Euler factors at infinity look like, but actually they are somehow products corresponding to the infinite places. And there's a different definition for real and complex places. And in some sense, the real places rule out half of the integers and the complex places rule out half of the integers. So if you have both at the same time, then there are simply no critical Hecke characters at all. And this leads to somehow, if you're interested in something like the Deligne conjecture for Hecke L functions, it means that we just have to study two classes of fields, either totally real fields or totally imaginary fields. Okay, and now let's say something what is known about critical Hecke L values. So what can we say about this question? What is a critical L value, or somehow what is the right period to divide a critical Hecke L value by to get something algebraic? And for totally real fields, this question somehow has been solved a long time ago. So let K be a totally real field and chi a critical Hecke character of conductor F. And I already made this observation that if there are many units in your number field, then there are not many infinity types, possible infinity types for Hecke characters. And of course, totally real fields are among all number fields the ones which have in some sense the most units, just because you have the Dirichlet formula for number of units. And so relative to the degree, the totally real fields have as many, or the degree of the units is as large as possible. And this somehow forces that the infinity type is always of form multiple of a norm type. And so you can always write an algebraic Hecke character in the form chi equals chi 0 times norm type, where chi 0 is finite. Then theorem of Klingen and Siegel tells us that these L values, if we divide by a suitable power of 2 pi I, give us something algebraic. And here I didn't make this W chi explicit, but in some sense it only depends more or less on the infinity type of the Hecke character. Okay, before I somehow, okay, this already settles in some sense the Deligne conjecture for all Hecke L functions for totally real fields, and we have seen that there are just two classes of fields, so let's now look at totally imaginary fields. In this case, I first need to introduce some terminology, so I would like to recall the definition of CM types, which often appear somewhere in the classification of endomorphisms of abelian varieties. So let's recall the following definitions. First of all, a CM field is just a totally imaginary field K0 containing some totally real field of index 2. So in some sense, these among all totally imaginary fields, the CM fields are the ones which are as close as possible to totally real fields, because there's a large sub-extension of a totally real field and then just a degree 2 extension which makes this field totally imaginary. And the CM type is simply somehow, we just have complex embeddings, they always come in pairs, and among all these pairs we fix one of those embeddings for every place. So a CM type is just a subset of all these embeddings, such that we can write all embeddings as a disjoint union of sigma and sigma bar. And now I would like to define or generalize this a bit. This is now just for CM fields. But if we have a totally imaginary field, we want to define a similar notion. And we say that a subset sigma of the embeddings is called induced by a CM type if and only if there exists a CM subfield K0 of K and a CM type sigma 0 of the subfield. So now here we are just in the setup. And then we just ask that the set sigma we want to define is given essentially by sigma 0. So we define, or we say sigma is given by all those embeddings which are in sigma 0 if we restrict to K0. Okay, so in some sense, these induced CM types just come from classical CM types by restriction. And okay, why is this related to Hecke characters? The point is, if we have now a totally imaginary field, chi a critical Hecke character of conductor F infinity type mu, then the set where the infinity type is negative turns out to be always induced by a CM type of a CM subfield. So in some sense, if we have a critical Hecke character of some totally imaginary field, then it automatically brings its own induced CM type. And this will be important. So any critical Hecke character of a totally imaginary field brings its induced CM type. And this is important because now we want to somehow say what are the corresponding periods for the critical Hecke characters, and the periods are related to certain periods of abelian varieties. So assume we have some induced CM type of some totally imaginary field, then we can use this set of embeddings to embed OK into C to the sigma. And since we have somehow fixed half of the embeddings here, this here gives a full lattice in C to the sigma. And the map is just given by lambda maps to sigma of lambda, where sigma runs all through all these sets, elements of the induced CM type. And so we have here a full lattice in some complex vector space. We can pass to the quotient and get some complex torus. And by CM theory, we know that there exists some abelian variety defined over Q bars such that the C points are exactly given by this complex abelian variety. And furthermore, since we defined here somehow the abelian variety using this quotient, and this lattice OK is somehow stable by the action of OK star, we can just decompose A by the action of OK, and we can decompose somehow the Colli algebra by eigenspaces of sigma. So omega A of sigma is just the somehow subspace of omega A where the OK star action is given by the embedding sigma. And you can already see this here on the complex picture because somehow here the Lie algebra is just C to the sigma and OK acts on each component here just by sigma because we embed here our element lambda using the embedding sigma. So already in the complex picture you can easily see that this here is in some sense this decomposition here, at least here on the Lie algebra. So we have this decomposition into somehow one-dimensional eigenspaces corresponding to these embeddings. And now let's fix a basis of each of these one-dimensional Q-bar vector spaces. So let's call these spaces omega sigma, and of course there's some choice involved, but any other choice will just differ by some element of Q-bar star, okay? And now we have the period pairing between H1 de Rham and the lattice. The lattice in this case is just OK. And inside H1 de Rham, of course, we have the first step of the Hotz federation, so we have these omega A's sitting in H1 de Rham. And then we can use this to pair omega sigma with some element of the lattice, and this lattice has some kind of distinguished element because 1 is an element of this lattice, and we simply pair everything with 1 to get some well-defined period. And these periods are actually just, these numbers are really well-defined up to multiplication by Q bar star because the only choice is more or less here the choice of the basis of these one-dimensional vector spaces. But we will see on the next slide that multiplication by some algebraic number will not change the statement of our main theorem because in the end we are just interested in algebraicity. So now we have somehow defined, so we started here just with some induced CM type, and in the end we got some set of periods associated with this induced CM type. And on the previous slide we have seen that if we have a critical Hecke character we get automatically an induced CM type, so in some sense we can associate to a critical Hecke character a set of periods through this complex or through this abelian variety with endomorphisms by OK. And this is now our main theorem in the totally imaginary case, so that K be a totally imaginary field, chi a critical Hecke character of this infinity type. And this here is actually no restriction at all, because we just write mu as the negative part and the non-negative part, and this was how we define sigma. Okay, so this decomposition is just alpha is the negative part of the infinity type and beta is the positive part. And with this notation, we can show that this, here, this should be 0, sorry, chi of 0 divided by this period is an element in Q bar. And omega chi is very explicit. It's just a product of powers of 2 pi I and these periods I've defined on the previous slide. Okay, and maybe one further observation here now, you might wonder, okay, here's some 2 pi i's showing up, but 2 pi I is of course also a period of an abelian variety because you have this Deschamps period relation. So you can in some sense say that up to dividing by a product of periods of a certain abelian variety, which is associated to the Hecke character, we get something algebraic. And I should mention previous results. So before, the case of imaginary quadratic fields has been shown by Demerel. The case of CM fields has, I think, first been shown by Shimura, but there's also a very beautiful proof of Nicholas Katz, and I also want to include him here. And certain extensions of imaginary quadratic fields, so if the Hecke character has somehow infinity type which is induced from some imaginary quadratic field, then there were some results by Colmes and more recently by Bergeron, Chalois, and Garcia. Yeah, and I should maybe also mention that a similar result has been announced in the 90s by Harder, and he gave a sketch of a proof, but the details never appeared. So somehow, I think there was some technical problem in the proof, but he sketched a proof, and so at least there's some strategy available how he wanted to approach this result. Yes, next I would like to say something about the proof, but so when I prepared the talk, I thought it's maybe also nice to say why previous proofs somehow failed, and also I think the idea of Nicholas Katz is really very beautiful, so I would like to explain you how his proof works, and this will also shed some light, at least in some simple examples, why periods of, say, elliptic curves or abelian varieties show up in such formulas. And therefore, I would like to start, so some of this is now from L-values to Eisenstein series, because Eisenstein series are always the bridge how you prove such a theory. And I would like to give this somehow how to go from L-values to Eisenstein series in the most elementary example of a Hecke character of some totally imaginary field. And therefore, we simply pick the most elementary totally imaginary field we could think of, just here the Gaussian number field, QH on I, and we take for F just the trivial conductor, so also the most elementary conductor we can think of. And then we always had this somehow infinity type, and this was related to CM types. And in the case of QI, a CM type is just we fix one embedding, and of course we should simply fix the standard embedding of QI into C. So we think about QI as embedded into C. And KB will be a positive integer which will show up now, because we define a very, very simple Hecke character. And this is some Hecke character you have not seen so far. So far I've only given examples of the form norm type times a finite character. And this is definitely not of norm type. We define it in terms of this classical definition. So we say, okay, a Hecke character is a multiplicative map from fraction ideals to C star. And now we take some fraction ideal A. And the reason why I've chosen QH on I is that this has class number 1. So every fraction ideal is principal. So we can write this as generated by some element xi. And now we just map this ideal A, which is generated by xi to the minus 4k. And why does the 4 show up? The point is, we have here some ambiguity in some of fixing this generator, but of course any other generator will differ just by a unit, and the units in QH on I are just the 4th roots of unity. And so the power 4 here will definitely kill this, root of unity. And so this here is really a well-defined group homomorphism from all fraction ideals to C star. And if you want to write this more in the form of, say, infinity types, we can say, okay, we apply sigma to xi. Sigma is just the standard embedding, and take here the exponent minus 4k. And this formula immediately shows that this is an algebraic Hecke character of infinity type minus 4 times k times sigma. So we have here the most elementary example of some Hecke character for the most elementary total imaginary field you could think of. And now, of course, the question is, what is the corresponding L function and what is the L value at 0? So let's compute this. L chi of 0 is just, we take here the sum over the values of the Hecke character divided by the norm to the S at 0, but this norm to the S at 0 disappears. And so the value at 0 is just this sum here, where we take 1 over psi to the 4k, which is exactly the value of the character at the ideal A. And here we sum over all non-zero ideals, but of course, so we have, of course, every ideal is generated by some element psi. So here the index set becomes the elements of this ring of integers, and the map from the elements to the ideals is, of course, 4 to 1, again, because every ideal here, there are somehow 4 different generators which differ just by the 4 roots of unity. And that's the reason why we have to divide here by 1 over 4 when we pass from ideals to elements. And now this looks very similar, very familiar, because this is essentially just the value of an algebraic Eisenstein series as at a CM point. So we have related here the L value to the value of some Eisenstein series at a CM point. But to really make this algebraic, we should not take this lattice, but the period lattice of the elliptic curve, because somehow, if you think about modular forms algebraically, then these are sections of omega to the tensor power k, and to trivialize this, we should fix an algebraic differential form. But if we want to write down the lattice in terms of the algebraic differential form, we are forced to take the period lattice. And that's the reason why this Eisenstein series is algebraic if we take here the period lattice and we get this formula. And the omega 4 to the k just appears because we have to write here the formula in terms of the period lattice, which exactly means that we get the power of omega 4 to the k in front of the formula. Okay, so this was, of course, just in a very, very simple example, but I think it might give you some idea, first of all, why this question is related to Eisenstein series. And the second point I wanted to stress here is that certain periods appear in this business. And of course, we used here many properties of this field, like it has class number 1, we used the units and so on. This was very special, but you can, with not much effort, somehow generalize this easily to more general imaginary quadratic fields. And so if you're just looking at imaginary quadratic fields, it turns out that the Eisenstein series which pop up, if you're interested in a very general Hecke character, will be certain Eisenstein Kronecker series. And so I don't explain how to go from general L value to this Eisenstein Kronecker series, but essentially you first decompose the L value in partial L values, and then you can avoid this problem with the class number, and you will end up with Eisenstein series of this form. But okay, the upshot is, in some sense, we can make sense of the previous strategy, but the Eisenstein series which show up in general are much more complicated and are of this form. And the Eisenstein series depend on certain integers. A is an integer bigger or equals 0, and B and N are positive integers. Lambda is some lattice spanned by omega 1 and omega 2. And S, you should think of S like a torsion section of the corresponding elliptic curve, so it's an element of 1 over n times lambda. And to these data, we define the following Eisenstein Kronecker series. So please ignore for the moment here this spectrum. Essentially, it's just we shift the lattice points by S, and then we take certain holomorphic powers and certain anti-holomorphic powers. And we sum over these shifted lattice points weighted with these holomorphic and anti-holomorphic powers. And this leads to the definition of my Eisenstein Kronecker series. Of course, you might say, okay, this only converges if B minus A is bigger than 2 or something like this. But then by a process of analytic continuation, you can actually make sense of these Eisenstein Kronecker numbers also for all integers here in this range. Similar, like the Riemann zeta function is first defined on some right half plane, and then by some process of analytic continuation, you get the values at all integers. And this A of lambda appearing here in the normalization is essentially the volume of the lattice divided by pi. So it's not important what it is. I just want to write it down for completeness. Okay, but now the point is, if we want to prove that, say, all critical Hecke L values of all imaginary quadratic fields are algebraic after dividing by certain periods, we have to prove the same statement for these Eisenstein series at CM points. And here's now a big problem, and actually it might be a good point to give up, because this map, viewing this here as a modular form, is not holomorphic in tau, because we take here complex conjugates of lattice points, and so it's obviously not holomorphic in tau if we do this definition, at least if A is bigger than 0. If A is 0, we essentially get an Eisenstein series, but if A is bigger than 0, it's not holomorphic anymore. And if it's not holomorphic, so okay, it still defines a real analytic modular form of weight k equals a plus b. But if it's not holomorphic, then the whole approach breaks down, because it was really important that our Eisenstein series was algebraic for the argument. And if it's not even holomorphic, we wouldn't expect anything like algebraicity. So it would be maybe a good point to say, okay, we give up here. But luckily, Nicholas Katz didn't give up, and he found a very beautiful interpretation of these real analytic Eisenstein series, which is in some sense algebraic. And therefore, let's consider the universal elliptic curve, E over the modular curve of level n, and write omega just for the relative Colli algebra and H1 de Rham for the first relative de Rham cohomology. And now let's start here with this sheaf omega tensor K where modular forms live. And okay, the first step is actually we map this injectively into some larger sheaf symmetric powers of H1 de Rham, just using here the first step of the Hodge filtration. And the advantage of this sheaf omega, of this sheaf H1 de Rham is that H1 de Rham carries a Gauss-Manin connection. And so we can apply this Gauss-Manin connection, in some sense, take derivatives of the modular forms we started with. And then we simply use the Kodaira-Spencer isomorphism, which identifies here the first scalar differentials with omega tensor 2, and here y is missing. And then we again use the Hodge filtration to map this to sim k plus 2 H1 de Rham. So in some sense, we use the Gauss-Manin connection to, in some sense, take derivatives of sections of symmetric powers of H1 de Rham, and we end up with sections in H1 de Rham in 2 degrees higher. And this allows us to in some sense to take derivatives of, say, something like omega of modular forms. And of course, we can iterate this. We start with some algebraic modular form, map it here, and then we can apply the upper row iteratively and get in higher and higher symmetric powers of H1 de Rham. And everything here in this line is purely algebraic, and also this is purely algebraic. Everything makes sense algebraically. But now the point is we want to get back to omega, and therefore we have to apply the Hodge decomposition. And this is the only point where we use algebraicity, because the Hodge decomposition is no more algebraic. But if we want to go back to classical modular forms, we need to apply it to get to symmetric powers of, or to powers of the sheaf omega. And then we get a map from omega k to omega k plus 1. And it turns out if we view these Eisenstein Kronecker series as something like, say, smooth or real analytic modular forms, that this map here just increases the holomorphic and the anti-holomorphic weight by 1. So in some sense, we can start here with something where A is 0. So this is some algebraic Eisenstein series. And then we apply this iteratively, and we get Eisenstein Kronecker series where somehow A is non-zero. So these are just real analytic modular forms. But in some sense, all these are just shadows of something which is actually algebraic if we view it here before taking the Hodge decomposition. Okay, so in some sense, these Eisenstein Kronecker series make sense algebraically, but they don't live in some power of the sheaf omega, but in symmetric powers of H1 de Rham. And the only reason why we don't see them algebraically is that we apply the Hodge decomposition. And now the next observation is, okay, the Hodge decomposition is actually algebraic at the endpoints. And now if we take the value at the endpoints, we get a proof that these Eisenstein Kronecker series at the endpoints are algebraic. And this, in some sense, finishes more or less this proof strategy in this case for all critical Hecke characters, because we have justified that these values here, okay, after dividing by a certain period, but again, this just comes from the fact that we have to take here the period letters are algebraic. And in some sense, the same proof works for CM fields, because we simply replace here the universal elliptic curve by the universal abelian variety with real multiplication. We work in the Hilbert moduli space. We still have CM points, and everything goes through. We simply start instead of with Eisenstein series with Eisenstein series, or with Hilbert Eisenstein series in this Hilbert moduli space. And this is in some sense the reason why these proofs only work for CM field, because I will say something about this in a second, but if you want to relate L values for more complicated totally imaginary fields to something like Eisenstein series, you get Eisenstein series which live on some space which is no more algebraic. And algebraicity was here crucial, because we wanted to say, okay, we take more or less values of something which is algebraic on some algebraic moduli space to get the algebraicity. And that's the reason why I think this proof has never been generated from CM fields to more general totally imaginary fields, because this strategy of proof somehow breaks down. And this is somehow the last observation, that this does not work over arbitrary totally imaginary fields. Now let's see. Okay, I still have some time. So let me say a bit about our strategy of proof for general totally imaginary fields. So I can't say much, but let me say at least somehow, let me explain the key steps. The first step is just we want to relate, again, partial L values, and partial L values is essentially that we fix here some class in a certain ray class group and just consider ideas in this ray class group. But this is not super important. The important thing is that we can relate these L values again to something like Eisenstein-Kronecker series, but also for arbitrary totally imaginary fields. And that's just a straightforward computation. This is nothing deep. And the Eisenstein-Kronecker series looks similar like the classical Eisenstein-Kronecker series, but here we have to divide by the units, which don't show really up in the imaginary quadratic fields, because this group is always finite and we always pass to some maybe finite index subgroup, so you don't see these here in the case of, say, totally or of imaginary quadratic fields. And again, alpha and beta are essentially the infinity types of our Hecke characters. So alpha is the negative part, so maybe chi of infinity type minus alpha plus beta. And this here, alpha is in set sigma and beta in. Okay. And these are the numbers alpha and beta showing up here. So once we have related this L value to Eisenstein-Kronecker series, we just have to prove that these Eisenstein-Kronecker series are algebraic, at least if we take here something like the period lattice instead of this algebraic lattice. This are also somehow, these are the Eisenstein-Kronecker series, which in some sense don't live in any algebraic moduli space, so this causes the problems. And our strategy of proof is, okay, so Nicholas Katz somehow took an abelian variety, say at some ECM point, and then deformed it or worked in the moduli space, and took a differential operator which lives on the moduli space to take derivatives of the Eisenstein-Kronecker or of the Eisenstein series. So it was really crucial that he works on some, say, deformation or some moduli space with an algebraic interpretation to take derivatives. And our idea is somehow completely different. So somehow we work over with a single abelian variety A, and A is really just the abelian variety. So as A, we take here the abelian variety we have studied before. So the abelian variety with C points given by C to the sigma mod our ring of integers. This is the abelian variety we are studying. And now we work just on this single abelian variety. We don't embed it in any family of abelian varieties, but we just work over this abelian variety, say over spec Q or Q bar, or maybe some ring containing Q bar. We actually, everything also works if we take here maybe some model over some subring, yeah, whatever. But let's, for this talk, let's just work over Q bar. But now we take a different geometric object to take derivatives. So there's this dual abelian variety which somehow classifies line bundles of degree 0. But this A dual also has a universal vectorial extension. So there's somehow a map from A dual or to A dual from some object A natural, and this is the universal vectorial extension. Of A dual, and this also has a nice geometric interpretation. It classifies line bundles together with an integrable connection. Okay, line bundles plus integrable connection, and that's somehow the object we work on. In some sense, we work in some sense on A dual, and the derivatives are somehow taken with respect to this connection in the universal situation, because somehow on A times A dual, you have here the usual Poincare bundle, but then you have here a map from the universal situation which classifies line bundle with a connection, and here you have some Poincare bundle P natural together with some connection, which is in some sense the universal line bundle together with an integrable connection. And that's more or less the situation we work on. So we don't add the abelian variety into a family, but we work instead with the abelian variety and the universal vectorial extension of the dual. And this leads to something like a completed Poincare bundle. So the completed Poincare bundle is in some sense sees only the information which is infinitesimally around A. So we take the completion of the Poincare bundle along the embedding of A into the A times the universal vectorial extension. This gives us some sheaf on A. And then we construct a certain equivariant cohomology class. We have our group OK star. So the units act on the whole geometric setup. And we take here a certain finite index subgroup of OK star. And maybe if OF star contains some torsion, then we pass to some finite index subgroup, which is torsion free, but this is not super important. But at least we have some equivariant cohomology class with values in this completed Poincare bundle with a connection. And how is this constructed? This Eisenstein-Kronecker class is constructed by a certain localization sequence. So we take some auxiliary ideal C, we take A minus C, and then we have this open embedding into A. And now here G is just the degree of our abelian, or the dimension of our abelian variety. And if you think about the localization sequence, the next step here is the cohomology with support in degree AG. And AC has somehow codimension G in A, and so you can really make this explicit what the next group here is in the localization sequence. And then you can prove that this map here is injective because you can compute the group which comes here explicitly. And then it turns out that you can somehow simply write down a class here by giving it residue under the localization sequence. And this is how we define this Eisenstein-Kronecker class. So in some sense, it's just a residue condition which defines our Eisenstein-Kronecker class. And the last step is somehow we want to relate this Eisenstein-Kronecker class to the Eisenstein series constructed in step 1. And this is a kind of lengthy computation. And we also have to take into account that the differential operator of the universal Poincare bundle with a connection, okay? So in some sense, this connection allows us to take derivatives of classes we constructed here, and then we specialize here at T star at some torsion point R, and you should ignore this. I decided to drop this from the notation, so this just survived from some previous version. But anyway, after some computation, you get actually something in. Okay, first you get something in, you get something over spec Q bar because we have just chosen here some torsion point to specialize. And you get equivariant cohomology in spec Q bar with respect to this group which acts of this, say, Q bar vector space. And here it's really crucial that we work with equivariant cohomology, because if we wouldn't work with equivariant cohomology, we would just get a cohomology class on some affine scheme, and this would just vanish and we would get 0. So it's really crucial that we work with equivariant cohomology. And since somehow the cohomology of spec Q bar vanishes, the spectral sequence relating these two things and some computations allows us to get something which is just in group cohomology of the group which acts on this Q bar vector space. And if you just look on this side here, this is actually quite similar to the sheaves or to the values where Katz's class is lived on. It's something like symmetric powers of H1 de Ram, and maybe, okay, we also have some powers of omega here, but if you want, we could also embed them into H1 de Ram, then we get just something which lives in symmetric powers of H1 de Ram. And the last step is, okay, this here, as I said, is a group, also the rank of the units. So our field K somehow has so maybe K has degree 2G, so the units OK star have degree, or the rank of the units is G minus 1, which is exactly the degree we take here. So we take, in some sense, the cohomology of some free abelian group of rank G minus 1 in top degree, and this can somehow be trivialized, and in the end we just end up in some Q bar vector space. We choose a basis, and we prove that in terms of this basis, the values of these classes are just the Eisenstein-Kronecker series. And since we are in Q bar vector space, we get just algebraicity from the fact that we are developing everything in terms of a Q bar basis. So this is more or less the idea of our proof. And now I think I still have a bit of time, so let me say a bit about one application about the construction of p-adic L functions for totally imaginary fields. Because our main theorem is something like the L value becomes algebraic by dividing by a very explicit period. And now you have these algebraic numbers, and we just fix an embedding into, say, CP, and then we can ask, is there a p-adic function interpolating these algebraic numbers? And that's what we do. So first of all, I should maybe say something about p-adic Hecke characters. So the definition of a p-adic Hecke character is just, again, some continuous homomorphism from the ideal class group to CP star. And now, any such character factors through the profinite completion here, just because the topologies here somehow forces that this factors through the profile completion, but by class field theory, this is just the Galois group of the maximal abelian extension of K. And it's also not difficult to see that somehow if we map here continuously to CP star, we essentially just see the P part of this Galois group, so everything will factor through some finite conjecture away from F from P and some P infinity. Okay, so any such character factors through this. So in some sense, we can think about p-adic Hecke characters just as p-adic one-dimensional Galois representation. And to any such classical Hecke character, so if we have a classical Hecke character, it's not difficult to see that one can construct a p-adic avatar. So if we start with a classical Hecke character, we get some p-adic Hecke character. Yeah, one can just construct this. It's not super complicated. And now let me say something about construction of p-adic L functions for totally imaginary fields, but under some ordinariness assumption for the primes. So let K be a totally imaginary field, Sigma-induced CM type, and P is now an ordinary prime, and ordinary means that the corresponding abelian variety has good ordinary reduction at A. Okay? And maybe I just say something about this condition in the case of imaginary quadratic fields. What does this mean for the prime P? So in the case of imaginary quadratic fields, you can show that this is equivalent to the fact that the prime P splits in the imaginary quadratic field. And if you have seen constructions of maybe p-adic L functions for imaginary quadratic fields, you might also know that the case of the prime P splits is much easier and much more is known in this case than in the inert case. In the inert case, things are much more complicated. And this more or less corresponds to the prime P split, but now for a totally imaginary field, and geometrically it means that the abelian variety has good ordinary reduction. And now our theorem is, okay, let's choose an auxiliary ideal coprime to P, and this is really necessary. I will say something why it's necessary in a second. And then we prove that there exists a continuous CP linear map from continuous functions on the Galois group to CP. So in some sense, we first look at this space, which are continuous function on the Galois group to CP, and now we construct a continuous CP linear functional on the space. So if you're familiar with the language of p-adic measures, that's just the p-adic measure. So we construct a p-adic measure such that for all critical Hecke characters chi, we have the following interpolation formula. So I missed here some explicit constants, but essentially it is the formula of the following form. We take the L value L chi of 0, divide here by this period in our main theorem. We have to remove the Euler factors at P, and we have, here's now also some term missing, we have to regularize. So this is, no, it's not missing here. 1 minus chi c times n0. This is somehow the kind of regularization term, and I will say something about this in a second. And the point is that this value here, which is a priori complex, is algebraic. We can embed it in CP and relate it to some purely p-adic number, but we also have to divide this number here by some p-adic transcendental number. And the period appearing here is really just the p-adic period, more or less, of the p-divisible group corresponding to the abelian variety. Okay? And previous results in this direction for imaginary quadratic fields, so I just mentioned here some results. I think there should be many more people mentioned here, but I think first maybe these constructions for imaginary quadratic fields and the prime P splits has been given by Manin and Wischig. And Nicholas Katz somehow generalized, again under this ordinariness assumption, this construction to CM fields using his proof of algebraicity. And maybe the last point I would like to address is, okay, maybe before I go to this point, I wanted to say something about this regularization. So the point is, without this here, the numbers here on the right-hand side might have unbounded p-adic denominators. And in some sense, you need this regularization, which in some sense kills this pole at the trivial character in some sense. This is like if you have seen maybe Kubota-Leopold p-adic L function, you also regularize to kill the pole at s equals 1. And this is somehow more or less the rule of the role of this regularization process here. And the next thing I would like to maybe emphasize is, why is this ordinariness condition here important? And here the point is somehow that that A or P ordinary. So say we have, this implies if we take maybe some model of A which has good reduction at P, that somehow A, the formal completion over some p-adic ring becomes at least over some large extension isomorphic to something like a chief power of the formal multiplicative group. And why is this good for p-adic interpolation? Because there's this theorem of Mahler which says that some of functions, if you have a p-adic ring R and you take functions on the formal multiplicative group over R, and that then you have an isomorphism of algebras with p-adic measures on set P with values in R. And p-adic measures are just somehow set P linear homomorphisms from continuous functions on ZP with values in ZP to ZP. So what we construct is in some sense a p-adic measure but with values in OCP on the Galois group. This is exactly here our functional. And the point is why this geometric condition is important, because we first construct something like a function on the formal completion, and then we apply Mahler's theorem to go to p-adic measures. This is somehow how we end up here with the p-adic measure. The intermediate step is to really use Mahler's theorem. And let's see, still a couple of minutes left. So now you might wonder, can you generalize this theorem to maybe more general primes? So this is of course some restriction because it just applies to primes which are ordinary, and this ordinariness assumption can also be described in terms of splitting behavior of primes, similar as the imaginary quadratic field. The splitting condition is a little bit more complicated, but you get just p-adic interpolation for primes with this nice splitting behavior. And the question is, can you maybe generalize this to more general primes? And in the case of imaginary quadratic fields, so I think if you drop this ordinariness condition, not even in the case of CM fields, anything has been constructed. So I think the only thing we know about non-ordinary primes where p-adic L functions of this form have been constructed is in the case of imaginary quadratic fields. And there have been several works. I think the most recent one is due to Andreatta and Jovita. But before, for example, there's also work of Schneider and Teitelbaum. And this work of Schneider-Teitelbaum is very interesting because in the case of elliptic curves, somehow if you take E an elliptic curve with Cm, Cm by OK, then the formal group associated to this elliptic curve can be somehow more or less there can be two cases. Either it's just something, at least after some extension, isomorphic to Gm hat, or it could be a Lubin-Tate group of height 2. And this formal multiplicative group exactly appears if P splits. And this appears if P is inert. Okay, and so if we are here in the split case, so in the case of ordinary primes, then everything is easy because we have Mahler theorem. If you're in the case of Lubin-Tate groups, things are more complicated, and you might ask, what kind of characters or what is somehow the interpretation in terms of measures or distributions for a Lubin-Tate group? And this question has actually been answered by Schneider and Teitelbaum, because they have shown that a Lubin-Tate group, if you pass all the way up to OCP, classifies more or less, or the functions on this Lubin-Tate group classify locally L-analytic distributions where L is exactly the field acting on our Lubin-Tate group. Okay, so this is this theorem of Schneider-Teitelbaum, and Schneider-Teitelbaum used this to construct p-adic L functions here for imaginary quadratic fields if the prime P is not ordinary. And this is actually something which is work in progress, what we are now doing in a work in progress with Guido Kings. We approach the non-ordinary case, and the important geometric input is exactly a generalization of Schneider-Teitelbaum theory to things like formal completions of abelian varieties. And actually what we could prove, and this is already available, is using more or less the classification of p-divisible groups or OCP, that more or less every p-divisible group or the rigid analytic fiber of a p-divisible group has an interpretation in terms of a character variety. And so we also have an interpretation of the p-divisible group associated to an abelian variety without any conditions like being ordinary over OCP. And it turns out that it classifies something which we call sigma analytic functions, which are some of functions which locally are just built up by embeddings using of this Cm times sigma. And so we can construct some p-adic L function in the non-ordinary case. We are about to write this up. But the point is we cannot somehow get a interpolation formula for all Hecke characters, but just for Hecke characters with a very particular infinity type. But still we get p-adic L functions in the non-ordinary case. And I think even in this case of CM fields, this is new. I think this hasn't been constructed before. And I guess the reason is that the missing piece was somehow what is the geometric interpretation of A hat in terms of characters, like Schneider title point interpretation of this formal completion. Yeah, and I think that's a good point to stop. So thank you for your attention.
Thank you very much for an enlightening talk. Any questions for the speaker?
Can you say again, like what's the difficulty like in the totally imaginary fields compared to CM fields?
Yeah, so I think the first difficulty is maybe that the Hecke characters are much more complicated. So in the case of totally real fields, we simply have finite characters times norm type. And so in this case, we have very simple Hecke characters. In the case of totally imaginary fields, Hecke characters are more complicated. And the next thing is somehow that the periods you would expect to show up are related, say, to abelian varieties. And this also somehow, the periods themselves are also more complicated. And so I guess this is the reason why the totally imaginary case is much more complicated. And I guess why the general case is more complicated than the CM case is what I explained, that you have this nice modular interpretation and can take values at CM points of certain Eisenstein series. Yeah, so maybe this kind of explains why the different cases are of different difficulty. Yeah.
But it's still like evaluate.
You mean for the p-adic interpolation, or no, or the
no, just for the special values.
For the special values. Yeah. So in some sense, if you want somehow. So, okay, I'm not sure if I write this now down exactly the right generating function, but I think something like derivatives of 1 minus, or maybe something like this, some very simple rational function with respect to, I guess, 1 over 1 plus t d by dt gives you more or less Bernoulli numbers. And Bernoulli numbers are essentially the values of the Riemann zeta function at the negative integers. And so this function here is actually a function which lives on Gm without 1, because it is a polar t equals 1. And so this function on Gm, so maybe I didn't write the correct function, but at least there's a function on Gm whose derivatives with respect to the invariant differential form, I think I should write like this if I'm not in the formal proof. But some function on Gm, when you apply the invariant differential operator to this function, gives you the Bernoulli numbers. And so in some sense, this is more or less a proof of this algebraicity theorem of Euler in the case of Q. So in some sense, you can make this into a full proof of Euler's formula, starting from this function. And so in some sense, the object for Q is more or less Gm. And for totally real fields is something like, I think maybe something like Z from OK to Z tensor Gm, where this tensor product is really more or less tensor product on the functor of points. And this is still a very simple geometric object, and you can construct similar rational functions, for example, using the work of Shintani. And this, I think, is maybe one explanation why it's much easier in the totally real field, because the geometric object is easier. It's in some sense just a product of GMs, and then everything is much easier. Yeah.
Thank you.
Any other questions?
So in the case of imaginary quadratic fields, is it possible to kind of compare your proof and Katz's and kind of
to compare? That's a very good question. In some sense it is, yes. The point is somehow, okay, this is something I also should have said. So the idea to work with the Poincare bundle came from work of Banai and Kobayashi, because Banai and Kobayashi constructed a certain Jacobi theta function in the Poincare bundle of an elliptic curve. So Banai Kobayashi constructed a certain generating function, two variables, say s and t, and I think it's something like sum over maybe a, let's see, I guess a should be bigger than 0 and b bigger or equal 0, and then something like e a b star, I guess maybe divided by some factorial, so maybe normalized, so maybe here some rational functions, rational numbers which normalize this correctly, and then you take something like s to the e t to the b, and I think you also have maybe here plus a certain pole at s and plus a certain pole at t, something like this. At least this is some kind of Jacobi theta function of the classical Poincare bundle, and they proved that this Jacobi theta function is a generating function for isosynchronous series. So in some sense, this was motivation for us to look at the Poincare bundle, because in some sense, the Poincare bundle in case of elliptic curve knows about the isosynchronous series. And what you're asking for is more or less, I guess, some question like, we take now the elliptic curve in the universal family, we take the dual elliptic curve, or maybe the universal vectorial extension also in the family, and here we want to compare the differential operators. And the point is, if you do this in families, then you can take the derivative in the tau direction, which is related to the Gauss-Mani connection, but you can also take the derivative into the s and t directions, which are somehow the directions of the elliptic curve and the dual elliptic curve. And now there's a heat equation of this theta s and t, which it does exactly this. I think the derivative in the tau direction is exactly taking the derivative in the s and in the t direction. And so in some sense, it's a heat equation for the theta function, which geometrically compares these two proofs. Yeah, but I think I only worked this out in the elliptic case. Maybe you can also work it out in the CM case, but I've never studied the heat equation and the corresponding theta functions explicitly. Yeah.
Other questions? If not, then
can you determine your critical Hecke L value in a precise field like the dimensional theorem can show if the Hecke associated to same elliptic curves, the value is lying in K. Can you show your value is lying in T?
This is also a very good question. So in some sense, this construction works wherever our abelian variety and some extra data for the abelian variety is defined. So in some sense, we get it. Everything just depends on the definition, the ring of definition of our abelian variety and some extra data which we need for the construction. So in some sense, we get final results. That's true. This is also important for p-adic interpolation because we want to have numbers which are somehow p-adic integral in some sense. So that it also applies where we need somehow this finer construction. But to get somehow, this is, okay, so I mentioned at the beginning the Stilin conjecture. And Stilin conjecture is actually a bit stronger than just dividing by a period gives you something algebraic, because it tells you also in which field, it tells you final rationality result. And in some sense, one can compare the periods we have written down to the periods in the Stilin conjecture. This has already been done by Don Plasius, and he has proven that these periods more or less can be compared. And so he has used this to somehow deduce from the results of Katz and Shimura the full Deligne conjecture for CM fields, for Hecke characters of CM fields. And similarly, somehow Don Plasius pointed us out that our results can be used to prove somehow the stronger form of the Deligne conjecture, where we really get the expected rationality. And this has been worked out by a PhD student of Guido King's recently. So in some sense, by again comparing the periods and doing some Galois descent, you get the full Deligne conjecture as stated by Deligne. Yeah.
Another question, like the p-adic periods. In the ordinary case, we know it is a p-adic unit, and in the non-ordinary case, it may not be a p-adic unit. How can you control the p-adic variation, like chi?
So in some sense, we construct a p-adic function, which is continuous in S, or which depends continuously in the characters, but only at the points where we have critical characters, we compare them to classical L values. This is somehow, but it's also a good question. In the non-ordinary case, these p-adic periods will not be units. They will have some non-trivial p-adic valuation, and this is maybe also related to the fact why you wouldn't expect to get a p-adic measure, because this would more or less imply, I guess, some boundedness of denominators.
Thank you.
If there's no more questions, then let's thank the speaker again.